Okay, so we finished this actually, but we are going to go back one more time. IP address is 32-bit, right? And in the beginning, when they gave out the addresses, there were only 4 universities, and they decided to give out 7 bits of network, and then the universities could select 2 raised to 24 addresses themselves. Your question.
Did they take an advance to do the 0 thing and do like the tree encoding?
The tree kept going. The tree kept going. They started ABC and then ABCD. Nobody really wanted B and C anyway in the beginning. So all the big universities are not the big university. All the initial universities had A grade, A class. Then the other universities came in, they got B class. Then people started getting C class, the companies. And some countries have only C class now, whereas some universities have A class.
They thought of the Hoffman encoding, like the Hoffman encoding of the prefix.
Yeah, okay, yeah. The question is the prefix encoding. Yeah, the prefix encoding was done deliberately that way from the beginning, so that the coding here is that if the first bit is 0, then it is class A, then you don't look any further. If the first bit is 1, then you have to look for one more bit. If the next bit is 0, then it is class B. And then if the next bit is 1, then you have to look more. Third bit is 0, then it is class C. If the third bit is 1, then it is class D, and so on and so forth. So this is, he says, Huffman encoding, and that is one common method of encoding the headers, such that you know how many bits to look before you can decide what class it is. Yes. All right. So then actually a new development happened, and that was the Ethernet. With Ethernet, you could have many computers connected to one interface. Previously, you had one interface per computer. And so then they invented the concept of subnet. This whole thing is a subnet. And here actually there was no subnet, because when the packet came, it was addressed to a computer and it will go to that computer. Here, if the packet comes and it is addressed to this computer, it will be basically broadcast on this subnet. And so everybody will know that a message came to this computer. Everybody can listen to that message in some sense. So subnet is one Ethernet, right? Okay. So let's revisit the addressing. Each network has a prefix. So this network has a prefix 128.10, and assume that this is 16-bit. This could be less than 16-bit, but let's say it is 16-bit. Then all addresses that have the first 16-bit like this belong to this network. This one is another network which has a prefix 128.211, 16 bits. So it will have many computers which start with 211. This will have many computers that start with 128.10. This network is numbered 10, and so this is only 8-bit. Right? What class is this? A class. This is an A class network, and this will have many computers which will have addresses like this. They don't have to be all zeros, they could be 10.10 point something something, you know. It could be any number there.
Why is it A?
Huh? Why is it A? Whereas only 10 bits, only 8 bits are specified, and the rest of the bits are left unspecified. The prefix length is 8-bit. If you go back to the previous one, this is the prefix length, 8 bits. 24 bits are unspecified. 24 bits are up to the network people to decide. Right? If it is a class B, then the big authority, the Internet Authority, IANA, they specify 16-bit, and then your you as a company can assign 16-bit to any of your computers, where the company could be a university, for example. If you get a Class C address, then you are assigned 24 bits. Those are fixed for you, and you can have 256 computers. You can assign any way you want. So that's how the class works. Classes means that you are assigned a prefix by IANA. Okay, so this is class A. Now here is another one which is class C. We have A, B, and C. This is C. This is 24-bit assigned, and remember, this is not okay. This is not a private address, by the way. Even though it starts with 192, 192.5 is not 192 point what? What is the next number? 168 is private, but not this one. So anyway, so this is a public address of some network, and this is a class C network. It could have up to 256. Now I'm going to come to your question 1 minute. So all IP hosts have a 32-bit address, and you can write them in 32 bits like this. So 128 becomes this 128, 10 becomes like that, 0 becomes like that, and 1 becomes like that. So you can write any IP address as 32-bit. Once you write it down as 8-bit each for each of those 4 decimal numbers. These are decimal numbers. 128 is not hex or anything. It is decimal number. And that's why we use the word dot. Dot is for decimal. If I use a colon, right, which is not used in IP, by the way. If I use a colon, then that is for hex. Okay, that is used in what? Ethernet. When somebody specifies a Ethernet address, how is the Ethernet address specified? 0A colon 0B colon 0C, something like that. Those are hex numbers separated by colon. IP guys decided to use decimal numbers, and therefore they put a dot. Yeah, the question here?
Yeah, so since as the classes go down, like A, B, C, D, E, you see the countries have, like some countries have class C. That means they have like a tiny amount of actual like IP address they can give out.
Yeah.
Is that what it means?
Yeah.
So like, what kind of a country could have only 8 different IP addresses?
I know. I'm just making it up. Actually, the thing is, that would be a really tiny country like Sikkim or something, Bhutan or something. But the thing is, no, actually, the problem right now is that while some universities have more addresses today than some countries. Okay?
The lower class you are, the less number of IP addresses you can give out.
Huh?
The lower class you are, the less number of IP addresses you can give out.
Yeah, the less number of IP addresses. Now you cannot even get class C. I think class C would be difficult, so we can get one address. So the thing is, IANA gave some addresses to AT&T, and when I get a DSL connection from AT&T, they give me an address, and they don't even give me that address permanently. They give me dynamically. So they might give the same address to somebody else next day. So now the addresses are in big shortage. All right. So going back to this, so each network has a prefix which was given to them by IANA, and the network manager can give the addresses out to its computers. So this network manager can manage 2 raised to 24 addresses. This can manage 16 addresses, 2 raised to 8 addresses. And when the routing is done based upon the prefix. So when a packet is coming from here, and this router will have an entry which says any packet going to 10 has to be given to this side. So it will not match the whole address, 10.0.0.49, it doesn't care. As long as the first byte is 10, as shown here, at least in this case, there is only all addresses beginning with 10 and a prefix, basically of 8-bit will go here. For this router, all addresses which have 192.548 first 24-bit like this will go here, and so on. That's why there is a prefix match. So everybody with the open computer in the back, please make sure the computer is either closed or you are really looking at these slides and are with me, because if I see you doing something different, I mean, I'm deducting points here, okay? Please, and I will ask you a question. So I have a question for you. What is the entry, what are the entries, two entries in this router? There are two entries in this router. What is the first entry and what is the second entry? No, you.
The two prefixes, 128-16.
Slash?
Slash 16.
16, good. And the other entry will say 128-11/16. So if it is matches these 16 bits, it will send it that way. If it matches these 16 bits, it sends that way. Good. All right. So all of these hosts, so that's how the network basically, saves the number of entries, because if it kept one entry for every host, it will be just too many entries, right? So it just keeps a prefix. So let's talk about subnetting. So all the hosts on a subnetwork have the same prefix, and the position of the prefix is indicated by a subnet mask. So this is subnet mask. Now generally speaking, the subnet masks are always a bunch of ones followed by a bunch of zeros. So that is just like a prefix before, where you can say slash so many bits. But you could have, if you wanted to be crazy about it, you could put a 0 here, and that is a valid subnet mask. And you could basically design your network so that when that one ended with the address, matches the entry, it goes there. Although, so as I said, subnet mask is a more general form than a slash. With a slash, you could not put 0 in the middle someplace. With the subnet mask, you could divide the network addresses in a different way. Is that difference is clear to everybody? Is that with slash, you are saying that first n bits have to be looked at. With subnet mask, you could say, well, I want to look at first 8 bits, then I don't want to look at the 9th bit, then I want to look at the 4th bit, then I don't want to look at the 7th bit. So you could be very selective about which bit you want to look at. Yeah.
When you say slash 24, does that mean the first 24 bits are 1?
First 24 bits are actually going to be looked at, which if you are going to do with net mask means first 24 bits are 1.
So first 20 from the right?
From the left.
The left?
Yeah, everything is from the left. So first 24 bit would be 255.255.255.
Okay.
That's what you generally see in your computer. If you see your net mask, generally you will see 3 255s. Right? That is first 24 bit. That is normally the size of most subnets.
The first 3 parts the same? Is it the same subnet?
So the first 3 bytes are same for everybody in that subnet.
And anywhere else, it's a different subnet.
If you go to different subnet in your same networks, for example, here's the thing. Some of you might have more than one router in your home. Okay? In that case, you have more than one subnet. And on the first subnet, you might have 192.168.1. On the second one, you could have 168.2. Third one, 168.3 or something. It's arbitrary how you divide that thing. So you could use different net masks and so on and so forth. Right? In my home, for example, I have multiple subnets. So the thing to understand is that this is how the subnet mask works, is that you have a mask bit which does not have to be all ones, but generally is all ones up to a certain point, and then all zeros. So you take the address, end it with the mask, whatever comes out is what you will match with the entry. Yeah.
Well, we don't have multiple subnet masks.
Oh, why you will have subnet map? Okay, so here thing. Even in the home there is protection that I want guests to be able to use that part. I want me to be able to use that part. If you have protections like that, then you want to have different subnets.
Doesn't seem like different internal IPs. Like
Those are internal IPs. Yeah, those are internal IP subnets. Those are internal IP subnets. They're all private, but for example, I may not want the guest to be able to reach my server. They can reach a printer, but not a server, right? So if you want to do that, then the only way to do that is to have a different IP net. In fact, some routers even allow this possibility that you can have several wireless networks, one that can reach your server, and one is a guest wireless, which doesn't allow you to reach anything. You can just go to the internet directly. Yeah, question? You had a question, Subha? No, you have a question?
Yes, so this address on this slide is the destination address of the incoming data?
Yeah. So we only look up the destination address, we never look up the source address. Because we are only interested in where the packet is going, we don't care where it came from. Not in IP. In Ethernet we will in the next chapter. Any other question? Yeah.
Could you give an example, or you said in the mask the advantage for this on slash that it doesn't have to be a sequence of ones, right? Could you give an example of when it is useful, not used?
No, I have no example when it is useful. See, thing is, it is allowed, but it is not used. It is not useful. All right. So like you can make up an example, but it's not useful. Yeah.
The result of this operation is compared to
With
another end,
The result of this operation is compared to the entry in the table.
which is also an end between an address and a mask.
No. You are talking about this table which you probably did in your homework today. You see, I am talking about this operation itself. You take the net mask, end it with the address, and compare it with this here. So if you get an address, you end it with this, and if it matches this, then you take this action. Right? Okay. Any other question? All right. So after a while, it became clear that one reason why we have this shortage of addresses is because we gave classes. We gave people 2^24. We couldn't give them 2^23. 9 bits prefix is not allowed, but not allowed before. So they said we will allow any prefix length. And so that is called classless. So there is no ABC. You could get a 9-bit address, 9-bit prefix, and that is not A class, that is not B class. Right? So that is called CIDR. CIDR is CIDR. Classless inter-domain routing. And then basically you could be given any arbitrary length prefix, so the only address you cannot use is when you get the host part. The only address that you cannot use is all ones. Generally you don't use all zeros also. So you have, let's say, 0 through 253, 254, 255. Sorry, 0 through 255. If it were just 1 byte, then the number could be 0 through 255. 255 is all one host number. That is for broadcast. That means everybody in the network gets that packet. So that address cannot be assigned to a host. And 0 is generally not assigned either, because 0 is all zeros, null address. So the only address we assign is 1 through 254. and one is, now you could assign any of one of these 1 through 254 as a default gateway, and some of you have seen number 1 being the default gateway. You could have number 254, you could have number 2, you could have any other number as a default gateway, right? But you have 254 addresses, not 256. Okay. So as shown here, this is different from that picture here, but basically this is the subnet address. Sorry, this is the subnet address /23, means that the first 23 bits are specified, and the last, how many bits are not specified? 9 bits are not specified. 9 bits is up to the network manager. Network manager has how many addresses? 2 raised to 9 minus 2. Okay, you won't use zeros and you won't use all ones.
Why can't you use all zeros?
Well, I mean, all zeros can be used actually to give you the answer, but this is just like null address. So I mean, like, you can probably reserve it for nulls. So either one is actually a question mark. If I said non-zero, all zeros you cannot use, some people will contradict that. So I mean, I would keep that as a question mark. But all ones cannot be used for sure. All ones is for broadcast. All right, so that brings us to the homework for C. Now you have 3 subnets, subnet 1, 2, and 3, and these are the prefixes. This one is 24-bit. Sorry, 24-bit is what the network manager was given. All right, so has the choice of having 2 raised to 8. 2 raised to 8 is 256 addresses, right? It has to divide into 3 subnets. Subnet 1 should have 63 addresses, subnet 2 should have 96 addresses, and subnet 3 should have 16 addresses. So now you have to divide the prefix such that they are adjacent allocation. Adjacent means you want to start from one end and then go. You don't want to have one here and then one there and have a gap in the middle. Yeah.
For the one that needs 63, so you need more than 2 raised 7. You need 2 raised 6 is 64, right? You need 2 raised 7.
Okay, sorry. Yeah, so let's just go with the notation here now, just to be sure. You can. So I will allow you to use zeros. So if you use zeros, then you will need 64. It was just 1 less than. So only 1 less than whatever number of bits you have, right? Not 2 less than, 1 less than. So if you allow for 64 addresses, that is only 6 bits. 96 is some number of bits, and 16 will require how many bits?
5 bits. 5 bits.
Okay, somebody is saying 5 bits. Those who are saying 4 bits, do you agree with 5? Alright, you need 5 bits. Alright, so 5 bits, 6 bits. So this is 63, so 6 bits, and then here you can calculate the number of bits. So that many bits. So somehow you put down this 256 addresses and chunk it out so that you get contiguous. That's the key. Contiguous or adjacent allocation. And otherwise there are many possibilities. With adjacency, it breaks it down to 2 possible answers. All right, everybody understands the homework?
I'm not sure. How do you write like those prefixes?
Oh, you write the prefixes just like this.
Yeah, but that's the entire thing.
Yeah, so you just write down something else, that dot something dash 23. Dash, sorry, not 23, it will be 25, 26, 27, something like that.
So say like dot 128, that will be 1 and all.
Slash,
the
yeah,
smaller number?
yeah. So you have to write down with the slashes, smaller number. and you can use 0. So only one extra address you need for broadcast. Okay, so let's correct that. Here I said that for 9 bits you have 2 raised to 9 minus 1 address, not 2 raised to 9 minus 2 address. You have 2 raised to 9 minus 1 address. One address is reserved for broadcast. Everything else you can use. So it's interesting. A friend of mine had a telephone number. It's like this: 314-596-00000, 4 zeros. I said, how can you have 4 zeros? He said, yeah, you go ask one telephone company, they will give you all 0 telephone number. So, you know, it's possible. You don't see it very often, but if you go to the phone company, they will give you all 0 phone number. Okay? All right, let's see. So we finished this homework. Okay, so next slide is this. So let's say you have routers like this, R1, R2, R3, and the networks like this, network 1, 2, 3, and 4. And if R2 sees a packet for network 1, what will it do? Network 1. It will say send it to R1. Because that's what this table will say here. If the destination is prefix is net 1, then forward to R1. If the prefix is to net 2, now these are all subnets. If it is net 2, then it will just deliver direct. Then it will not forward, it will just send it to the host directly. Similarly, here it will send it to the host directly. But if it is going there, then it will send to this router, and this router will send it to that one. So remember, the IP packet is going, it has a source address and a destination address. Nothing in the packet is changing. But as it goes hop by hop by hop by hop, at each hop, there is a header outside of IP, which is the layer 2 address, which is the Ethernet address. Right? That is changing at every hop. And that layer 2 address will be, in this case, it will be the address of R1. In this case, it will be the address of R3. In these two cases, it will be the address of the host. So we are not talking about the IP address, we are talking about the layer 2 address. This is confusing at this point because you haven't heard about layer 2, but the packet itself looks like following. It has application header. In front of it, it has TCP header. In front of this, it has IP header. In front of it, it has Ethernet layer 2 header. Right? In layer 2 header, there is a source and destination, S and D. In IP header, there is a source and destination. In the TCP header, there is a source port and the destination port. Is that clear to everybody? That every layer has a header, and every layer has a source and a destination. Right? So the layer 2 has a source and a destination, and that changes every time you go to a new link. So and there it will say packet is coming from R2 and going to R1, although the IP packet doesn't change. IP packet is coming from some place and going to some other place. So those remain same, but every time the router looks at a packet, it has to decide where to send next. That next part is put into the layer 2. Yeah.
Are those used for preventing loops, infinite loops, or?
Well, I mean, loop prevention is totally orthogonal to this. It's totally orthogonal to this. Basically, this is how the networks work, is that the layer 4 gets to layer 3 and layer 3 gets to layer 2, right? And every time you get to layer 2, you have to tell where it is coming from, where it is going. So layer 2 is only one hop. Layer 2 is always one hop, right? So the source for the layer 2 is for the router which is at the beginning, and the destination is the router which is at the end of this hop. Alright, so that's what this table tells it, is that please put this address on the layer 2 header and send it here. Yeah.
If you were at R1 and you needed to go to net 4, it would forward it first to R2, right?
Yeah, to go to net 4, the packet when it came from, let's say, first of all, this is the problem with the book, because book is doing top down. So top down, and there are other books which do bottom up. So they first cover layer 2 and then they go to layer 3. Here we are finishing layer 3, but we haven't done layer 2. So you have to remember what is in the layer 2. So when the packet starts from network 1, it will say it's going from some host in network 1 to some host in network 4. So those addresses will be in the IP header. Right? However, in the data link layer, the source address would be the source address of the host, the destination address would be the router 1. Right? So on that Ethernet, the packet will go to router 1, and then router 1 will look into its table, and the table will tell it that send it to router 2. So the layer 2 header will change. Now the layer 2 header will say it's coming from R1 and going to R2. IP address is still the same, right? But the layer 2 header will say R1 to R2. When it goes to R2, it will look up the same IP address, and that will say I have to send it to R3. So the data link address will change from R2 to R3. It's going from R2 to R3, right? And the IP address will still remain the same. It is going from A to B, right? And then when it goes to R3, it will look up the table and will say deliver to B, right? So then it will change, the source address is R3 for data link and the destination address is B. Alright, so although this is not in the slide, but it should be clear that these instructions only tell the router what to do with the layer 2 header. The IP header doesn't change. Actually, it changes in one field, which we have not discussed here, but that field is called time to live. Let me go back to that field. There is a field in the header called time to live. Actually, should be called hops to live. So you start a packet and you put a number 8. That packet will go only 8 hops. At every hop, that field is changed by 1, decreased by 1. And when that field becomes 0, the packet is thrown away. So that is what is used to prevent loopings, because somebody asked here, is that used for preventing looping? Time to live is used for preventing looping. But if you are looping around, then that field will become 0 very fast. Yeah.
But if it's looping, doesn't mean that someone configured it wrong?
Yeah, that it can loop. The packets can loop because somebody configured it wrong or somebody gave him wrong information. For example, I could give information that all the packets to X should go through me, and then I could send it back to somebody who would send it back to me. Yeah.
What if the destination is 9 hops away?
Yeah, so you have to be careful. So you cannot just put 8 hops and the destination is 9 hops away. So you really put a number that you feel is comfortable, and so you would put something like 255. Nothing is more than 255 away. The whole world is only 7 hops, by the way. So, so if you cannot make it in 14 hops, then you took a very long route. Okay. So that
Time to live is 8 bits?
time to live is 8 bits. Yeah. but it is decremented at every. So the reason I brought to this slide is for two reasons. First, somebody wanted to know how the looping thing is detected, and second thing is when I said that the IP address is not changed, IP header is not changed, and I felt that I was saying something wrong here. The IP header is changed, but not the addresses. TTL is changed at every hop. Yeah.
What do you mean the whole world is only 7 hops?
The whole world is only 7 hops in the sense that if you really went by the shortest route from here to China, Germany, any place, you can get there in 7 hops. Shortest route.
So what if you have like 6 routers inside your own subnet?
Of course. then you. I'm not talking about those special cases. Yes, of course. So that is not something which is guaranteed. I'm just saying that if you, let's say you didn't have 7 hops in your home, you got out of your home, then you go to AT&T, then AT&T can get to its provider and then get down to China and then deliver it.
So Trace also does the things are not that efficient.
Yeah, right. So this is not necessary. You don't always take the shortest route. I mean, it's quite possible that when you go to AT&T may not just take it and send it to outside. They might go 10 hops in their network, and then AT&T gives it to somebody else. They go in their network for 10 networks. But so a statement about 7 hops is false and true. In some sense, it's true because if you really took the shortest path, so maybe 7 networks you are passing through. But sometimes it will generally take much longer. So here I think let me just tell you this thing why it is. Just do trace route to Google, it will come out to be 13 or 14 hops. Doesn't matter from wherever you do it. So it's right there. It is false, right? How come the world is 7 hops and Google is 14 hops? The idea is you don't take the shortest route. You probably take the cheapest route, or the providers take the cheapest route, for them. All right, so that is TTL. Going back to where we were.
I had a question on the previous slide.
Yeah.
So is there a difference between forward and deliver? Because it's the same action for the router.
There is a slight difference. Forward and deliver. Actually, see, the thing is, yeah, I mean, it's almost the same. I mean, I don't see the difference between this one. So so tell you the fact, the table doesn't say forward and deliver. The table is already shown before. I mean, you have the table. Table is here, routing table. Right? It doesn't say what to do, forward and deliver. All it says is that this is the next hop and this is the interface, right? And so in this case, let's look at this address, for example. This is a deliver. What it says is that basically, if anything is 192.168, then just use that interface and drop it right there, period. It's on the Ethernet. All 250, all the addresses, they just go right there. This one is different. In this case, my computer actually has the address 106 and 108, but this is a router in the network. This is different, outside of my computer. So this is more like forward. Right? Although it doesn't say in English forward or deliver, but basically what it is going to different computer. So it says if some addresses don't match any of these and they somehow finally match with this, everything will match with that. So then they will be sent to 192.168.0.1, which means the router, and then the router will look it up and do similarly other way around. All right. Any other question? And those are all very good questions. So let's move to the next topic, which is the aggregation. Is that we don't keep what we do is when we have when we have multiple addresses on one interface, we try to combine them into one entry if we can. So let's say we have this address 0/23 200.23 16.0/23 and 223.20.0/23 and 223.30.0/23. So this, if it was a router, actually this is a network, will have these different addresses in their table. But when they come here, all these addresses will be combined into one entry. How they will be combined into one entry? The entry will be 223 and 16/20. So we don't care whether it is 16.0, 20.0 or 30.0, all of them are here. Okay, so this is called route aggregation. So similarly here, this one and this one has the address 223.18.0/23. So these have to be distinguished because basically this one will have the entry which will match 23 bits and this one will match 20 bits. So we take the longest prefix. So if something matches this, then we don't match with that one. Right?
What is the 223.31
223.31
0? Yeah.
31.0. So right now 31.0 will not match this entry, but it will match this entry hopefully. Right?
The ISP, but not any organization within the ISP.
I'm sorry?
So it seems like it'll match the ISP, so it'll go to the 5x9 ISP.
Yeah, it will go to that ISP.
Go to any organization.
And then will probably be dropped there, yeah, because there is no 31. But this entry will not tell it, right? Here it will match and here it will not match. Any other question? Yeah.
31 would be under organization 7, because it's a /23, so it's 30 and 31.
31 organization 7 30-0.23. So I have to verify that. So he's saying 31 is part of that organization 7 and we can verify that. Let's see, 30.0. 30 is 16 plus 14. So 14 is 8. This is wrong. 16 plus 14, 8. Now we have 6 left. 6 is 4, 2, 0, 0, 0, 0, 0. So this is too much. 0, 0, 0, 0. Is this 30? Am I doing it right?
That's 9 bits.
30 in 8 bits. 16 is right. 16 is right there. 16. This is 0. This is 2, 4. 2, 4, 8, 16. So this is 30. Right? And 0. Now we take the first 23. So first 23 will be right there. Right? So now 31. Now 31 will be 1, 1, 1, 1, 1. Right? And so that is part of the same prefix. 30. Okay? So that one is existing in this case. Good point. Thank you. Yeah.
I think your mic is off.
My mic is off. Okay. Maybe the battery is gone. Who knows? It does that. Yeah. There is nothing here. Okay. All right. So the thing is, when we get a 31, we don't look at these last bits. We just look at the first 23 bits, and it matches the 30. So the key part, this part was actually the key was other way around, is that given the addresses, can we find a common prefix? So that's what we will do, is that if suppose somebody gave us some addresses and we write them down, and then we see where is the common number and where the difference starts, right? Whatever is the common part, that is what we specify as the aggregated prefix. Yeah.
Where is this aggregation being done?
Oh, at every basically 2 places it is done for sure. One is done is when we talk about BGP and all that. So when you want to decide where to send it, and you could do it every router, but you generally do it for sure when you exit a ISP. Because when you do exit an ISP, then you decide which ISP to go to. It costs money, real money. And so you really have to have tables which go by these things.
Is the idea also to find the longest possible aggregation? Because you can always find short aggregations. Or almost always. 1 byte aggregation.
The longest prefix match. The question is the goal is to find the longest aggregation. I'm sorry, you could always find the...
Theoretically, you can decide, well, I will have 1 big aggregation. So we will have 2 options, everything will go in.
Oh, right, okay. You're saying that we could just call it 200/8
Yes.
rather than 223.6.16. Yeah, you could do that, and this will pass the test, but what will happen is many of these will be exceptions. So as long as you don't have too many entries table like that. So the thing is, you will have 8-bit matching 200, and all of them will go here. But there might be other addresses which are somewhere else, and so they will have entries too, and they will match for their addresses.
So you want to find the longest possible?
If possible, right now. So right now, what we are doing is, we are saying that when you want to aggregate, do the longest prefix, because we know for sure that most of things which are not in this are not in this direction. Okay. Okay. All right. So as I said before, on several slides, I have this thing in the bottom added, which is actually in your handout as well. So this is the section to read about this. Our material up to here. These are the pages and these are the problems. Now private addresses. We have gone through the private addresses before. Now we are going to go one more time, and you have to remember now much more clearly that the private addresses are anything beginning with 10, anything beginning with 172.16, first 12 bits only, not first 16 bits, first 12 bits. And so that could be 172.16 to 172.31. And then anything which has the 192.168. Okay. So if I give you a different address which is not 168, that's not private. 169 is not private, 167 is not private. Only 168 is private. Yeah.
What about the address that starts 169 something that you can't find an IP address?
Yeah, and that's an interesting one. They must have reserved some for some reason. I have to figure that out. So the question is that if you don't have a DHCP server, then suddenly the computer automatically assigns a 169 address. Where does that come from? Obviously, that cannot be a public address, right? And so they might have reserved some address in that range for some particular purpose. I have to see that one. All right, but here's the thing though, 172.17 is a private address, right? 18, 19, 20 up to 31, but 32 is not. Okay? Everybody understand that there are only three ranges that have been set for private: 10/8, 172.16/12, and this is 168/16. These two are very easy to check. This is kind of difficult to check. It's the whole range, 12 bits. And we already know why the private and public addresses. Private addresses have to be kept in the network. Only public addresses can get out on the internet, and we need a device in between which is called Network Address Translator, NAT. We talked about NAT earlier. And this slide actually is a replication of the previous slide that we already gone through. Is that how does NAT work? NAT takes all the in packets going out, changes. What does it change? Two things it changes. No, hold on. Let me see if anybody else remembers. Anybody remembers what are the things that NAT changes? What does it change?
The private address to a public address and the port to a different port.
Yeah, so it changes the source port and the source address. Source address is changed to a public address, and source port is changed to any random number which is not used so far.
And the way it changes the address.
And then it comes back, it looks at the destination port, and destination address is obviously the public address, so it changes this destination address to the local address, private address, and the destination port to the port which is remembered in the table. Right? Does everybody remember that, or should I go through that more detail? We went through NAT, I think when we were doing applications. So it changes the source port and the source address. The only problem with NAT is that if you haven't talked to somebody, they can't talk to you. So it's only outgoing access, not incoming access. If you want to do incoming access, then you want to register that port with the NAT box already, so that it has permanent table registered for you, that whenever somebody sends a destination port of this value like 80, 81 or something, it should be sent to this private address. Yeah.
How does this work for UDP?
How does it work for UDP? Same thing. Source, exactly the same thing. This is independent of TCP and UDP.
Now does it send back? Does it remember forever in the table? Or does it time out?
Yeah, so the question is, TCP at least there is a connection setup and connection tear down, and in UDP there is no connection setup. The answer is it is exactly the same for both. In TCP there is a connection setup and tear down, but the NAT box doesn't look at those messages.
So it's timeout.
Everything is by timeout. Yeah.
For one of these countries that you say has a class C, do they have a massive NAT on the entire country?
I don't know. See, I'm just making up the problem bigger than it is. I don't know if there is a country with Class C address. I'm just telling you right now, many countries are complaining. I mean, I can give you a big example. China. China has, I don't know, big population compared to United States, and has the addresses which are 1/1,000,000th of United States, something like that. So this is a big imbalance there. So they are really in big shortage of addresses, right? And so that is one big example. There might be some other countries, but they're not advanced. China is advanced, and they need all these addresses, and they don't have the addresses. So that's a big problem. So I'm just making it up, that some countries don't have it. Some universities have bigger addresses than China. So that's unfair, right? So that's what they're complaining about. Yeah.
So when your computer sends something out, the NAT remembers like maps, like the source port to the random port, and likewise the source address to the public address.
Yeah.
When the message comes back, does it like delete that entry in the table?
No. The table entry is not deleted because the second packet may come back.
So when is
Yeah, so when it is deleted, the question was when it is deleted by timeout. If some entry is not used for a long time, then you delete it. Okay? All right. So then there is a protocol called universal plug and play. So first, people said we can manually program. So you can go to the router and say, well, anytime this uTorrent port number comes in, please send it to me. Right? So you can program your router for a particular port to go to a particular computer. But that was manual and too much work. So they said, why don't we write a protocol so that any computer can send a message to the router and say, please put this port number for me. And that is called plug and play. UPnP, Universal Plug and Play. So, any host can request the NAT that I am expecting some packets from outside, and this is the port number on which they will come. And so that protocol is called UPnP. You can specify the port number, and then the NAT will make a table. So even before you send anything, whenever something comes to that port number, it will be sent to that particular host. Yeah.
What's an example of something that uses that?
Almost every application. Your uTorrent is using that right now. Your BitTorrent and everything else, because the thing is, if any application can expect a packet without announcement, for example, suppose somebody wants to get a piece of file that you have. So how do they get to you? You haven't sent them anything, so there is no table in the entry, right? But if somebody sends you, so you have this weird port number, 5-digit port number 32453, right? That's not a standard port number, but you decided that that's the port number you will use. You told these, whatever they call the seed, what do you call the people who keep track of all the seeds, tracker. You told the tracker that this is my IP address and this is my port number. But when somebody X wants to come in here, then they can come through this UPnP.
So it's mainly used for stuff where other people need to get information from you?
So basically for incoming connections. And this is just one example. There are other places where incoming connections are required. So whenever you want to have something, incoming connections which are not initiated by you, somebody else wants to initiate from outside, you register the port number with the NAT using this protocol. Yeah.
So, how do are there permissions with that NAT? How does?
Yeah. So first of all, when you buy a router and you go and program it, it will say to enable UPnP or not enable UPnP. So I'm sure Vashu probably will say do not enable. At my home I have said enabled, right? I mean, depending upon how much you trust your population or inside computers. You see what I mean?
So if I wanted, could I forward port 80 to?
Yeah, right, if you are allowed to.
Okay.
Yeah, you could request port 80, but then the people who are managing the NAT box would have said that port 80 is reserved and static and only for this computer, and then it is not allowed. It is quite possible that even by default, when you go to ask for port 80, it will say the port already assigned. So somebody has to deassign the port first before it can be assigned to somebody else. All right. So UPnP is basically that. This is just a protocol. We are not going to go into protocol messages, but at least now you know that there is a protocol where you can send a request to the NAT box and saying that please reserve this port number for me, and then it will just make an entry into the port in its table. And that way you can have servers inside the network, private network. Another common protocol is DSCP. And you know DSCP, eh? Go ahead, question.
Yeah, so for the previous topic, you have to also have a permanent address for your router. If that changes, then people from the outside will not know where your host is.
Okay, so let me go back. So the thing is, this thing will work only as long as your IP address remains the same. So, I mean, like when you went to the tracker and said, well, here's my IP address and here's my port number, people will come. If your IP address changes, all bets are off. Okay, so the
address of the NAT changes.
the one that AT&T gave you. So the solution to that is to not give out your IP addresses. For example, I have a dynamic IP address. So when I give it out to anybody, I don't give them IP address, I give them the name. Dynamic name, sorry, my name, which is not dynamic actually. And so the name for my host is jain.homeip.net. Okay. That name is fixed. AT&T can change the number, but every day what happens is my router goes to dynip.net. Okay. Over there reserves that name, says if anybody is looking for this name, please give them today's address. So every day their new address is registered with there, and anybody who wants to reach me can reach me anytime. So mine is almost like a static address. Address is not static, but the service is being provided by Dyn, whatever that is, Dyn DNS, yeah, dyndns.org, right? Dyndns.org provides this service that gives a name to your dynamic IP address. Once you do that, then you can open a website. For example, I can have a website which says, you know, jain@homeip.net/whatever, right? And anybody can log into that. And right now I don't have the IP address. I don't have that website. But I'm just saying that I could advertise that website, and anybody can reach that anytime, even though my address is changing. Is that part clear to everybody? That there is a service called dyndns.org which lets you register a name. And once you register a name, you can change the address every minute. It doesn't matter. When somebody wants to reach you, they will go and resolve the address. They are your DNS resolver. They will find the address, dynamic address, and your server will be up. Yeah.
You know, how do they get the DNS servers not to cache the responses so that if a server caches the old IP address, it changes?
Yeah. So the question is, if your IP address changes, how do the people know it? Well, basically they will use the old IP address. It will be rejected. Once it is rejected, then the next request will say, please give me a definite answer, not from your cache. When you ask for a definite answer, it will go all the way to the master. Yeah. Okay? Yeah. What is it that if somebody registers an IP address? So with dyndns, you need a password. So you cannot just go and say, well, here is the jain.homeip.net and here is my IP address. I have to go there, I have a password and username.
What if you get rid of an IP address, like you give it out, and then someone else uses that IP address regarding the cache?
Yeah, right. So what will happen is, for a short while, they will get the packet, but they will not know what to do with it. Well, here I think, I mean, so they will get, suppose it's my web server, so they will get some web request which says, please tell me what is your lecture for today, and they will not know what to do with it. Right?
There is another protection. AT&T will not give the same address to two different NATs.
Now, hold on. They can. They can, but generally they will recycle after 24 hours or maybe 6 hours or 2 hours or 1 hour. Minimum time they will put so that, you know, it's not that some connections are going on and suddenly they change in the middle of the connection and then now everything is going other way. So generally here is the thing though. This is the normal rule for DSCP. Actually we are in DSCP already. DSCP gives out the address for a day. But before the day is over, you can go back and renew it for another day. And it will preferably give you this previous address. So you can keep renewing every day and you will get the same address. If you turn off your router for 1 day or 2 days and then go home or go on vacation and come back, right, you will get a different address. But generally, if you don't turn it off, you keep the same address. Okay? All right, so let's go back to DSCP. DSCP is the dynamic host control protocol, and that is the one that is used to give you the temporary address that you need. It is used for both private addresses as well as for public addresses. Inside the home, you have a DSCP server because you want the computers to be able to connect anywhere, any place. When you bring to the office, they need 128 dot something something address. When you take it home, they need 192 point something. When you take it some other place, they need 172 point something. So people don't program any address in the computer. They leave it to figure it out. When they go there, first thing they ask is there a DSCP server here? If there is a DSCP server, it gives you the address for that network. So you are connected. You take it home, same thing will happen. It will say there is a DSCP server here. You get the address and that will work there. So you cannot really put any fixed address in your computer anymore. All right. So DSCP server simply keeps the list of all the addresses that have been assigned by their MAC addresses. MAC address is the Ethernet address, layer 2 address. And then when you go back, it preferably will give you the same address that it gave you last time, unless it has been given to somebody else. And it gives you for 24 hours or 48 hours or whatever. You can program all that in your router. So it gives you for that long, and you, before the time is up, you can go back and renew it. All right, so let's see. We finished everything on this slide. Dynamic host control protocol allows host to get an IP address automatically from a server. Do not need to program each host. Each host has a lease time, can reuse a limited number of addresses, and host broadcast, is there a DSCP server here? And DSCP server. So how do you find a DSCP server? That's a multicast address. So you send your message to that multicast address, and anybody who is listening to that multicast address is hopefully a DSCP server, and then will respond saying that I'm here and here is your IP address. Yeah.
That is 1111 is how the IP address is?
Okay. Question is the DSCP address that .111 means, you saw it here. This was class D address, you mean?
Oh no, I meant when you have a subnet, then if it ends with the all ones, you said that it broadcasts to the entire subnet.
Right. So we haven't talked about the Ethernet addresses, have we? No. So when we come to Ethernet addresses, then we'll talk about the multicast addresses for Ethernet. So similarly, for example, like IP has a multicast address. Ethernet also has a multicast address. And when you go on the Ethernet, you ask, so you use that multicast address and send the packet.
That means that everyone who's with you on the Ethernet network gets the packet?
Yeah, everyone on the Ethernet will listen to that. I mean, can listen to that, although most of them will be ignoring it, but the DSCP server will be listening particularly for that multicast address. Yeah.
Did you say the terminology here? A broadcast sends a message to a multicast address, which is
Okay.
every single thing I say.
All right, let me clarify. That's a good question. First of all, broadcast means for everybody. Multicast means a group. All right. So, for example, if I send a message, we don't have a group here, but let's make a class in the class two groups, left group and the right group. For some reason, doesn't matter. Then I could multicast to the left group. Even though there are right group people in the same room, they are not going to listen to it because they are not part of the multicast. See what I mean? So multicast means a limited set, and that limited set generally is by functionality. For example, to all DSCP servers, to all routers, to all bridges, to all, these are all multicast. If I say to all nodes, that's a broadcast.
So is DHCP a multicast or a broadcast?
This one is multicast. Okay, now I think the confusion is host broadcast, is there a DSCP server here? That yeah. Okay, so that can be then one of the two ways, and I have to check it now. One way is that I could broadcast a message, which means it will go to everybody and say that is there a DSCP server here, right? Or I could multicast the message, which says, you know, it goes to only certain people, and it says is there a DSCP server here. I think it should be multicast, okay? But I have to check if there is a multicast address for DSCP server. If there is no multicast address for DSCP server, then we can broadcast, right? But I think it should be multicast. So here's an example. The client arrives and okay, this is a broadcast actually. This is a broadcast. It sends the message to this address, which is 255.255.255. That's not a multicast, that's a broadcast. And it says whatever it says. It says, is there a DSCP server? Then the answer comes back, yes, here it is, and this is your IP address, and you have 3600 seconds. 3600 seconds is 1 hour lifetime. Sorry, DSCP offer. Offer basically says that I can, yeah, I am here, and then this one says, so okay, can you give me the address, and this gives the address. Okay. So this is actually broadcast address, not multicast address. Continue recording. Okay, I think this would start. No, sorry, we have 7 minutes. Okay, 7 minutes, 4 minutes. Okay, all right, we can stop right there then.